Hi, good afternoon. I'm Sarupuri. I'm from HitLab New Zealand, and I'm here to present my paper called TriggerWalking. It's a biomechanically-inspired locomotion technique, which is used for efficient, realistic virtual walking. So the main motivation is that locomotion is one of the most basic and universal interactions found in virtual environments. It is any change in the viewpoint of the user. But the problem is that it is a problem which has only half solutions, and till now there isn't a locomotion technique which is perfect in all scenarios for doing all sorts of tasks. So when we talk about movement, the first thing that comes to mind is to just walk. Physical walking is the most natural and obvious technique for traveling in virtual environments. Active walking can be expressed as repeated gait cycles, and in VR we have a couple of applications where we use real walking or redirected walking or scaled walking. But in the real world, we have only finite track space, but in virtual environment, we have an infinite space. So how do we map it? It's a big issue. So that's one of the drawbacks of using a natural locomotion technique like walking. And again, tracking is an issue because we can just track only a limited space, but we have infinite virtual environment, and prolonged use of any natural locomotion technique, take real walking. We don't want to walk for hours in virtual environments, which will induce fatigue. There are some techniques which use some gestures of walking, like walking in place, but even then, the prolonged use induces fatigue. And we have artificial locomotion techniques. The most popular one would be teleportation, but teleportation is notorious for breaking presence, and it is spatially disorienting. And we have joystick navigation where you just use the arrow keys to navigate in the direction, but because of the sensory conflict, it induces a lot of cyber sickness. So how do we measure a good locomotion interface? There's a statement which says that user interface is like a joke. If you have to explain it, then it's very bad. So, yeah. So we don't want people to hate a locomotion interface, or we don't want them to learn, or we don't want them to be tired. So these are the quality factors we came up with. The first one is speed control. We should be able to control the speed. One measurement would be the time, how fast, how soon you reach the target. And the next one would be positional accuracy. For some tasks, you need to be accurate. You need to move accurate. So, and the measurement would be, like, it depends on the task. In the experiment I did, which I'm going to explain in the next slides, score and collisions is the measure for accuracy and information gathering. So while moving, say, for example, if you take teleportation, we can teleport to a point which is in a distance, but you can't gather the information that's in the surrounding while teleportation. But some of the tasks, like navigating in a museum or some room, you need to gather the information. So that is one of the quality factor. So, and it should be easy to learn. It should be easy to use. And SUS score or system usability score is one of the famous way to get the usability scores. And also the preferences of locomotion techniques would be one of the measure for easy to learn or easy to use factors. And we don't want a locomotion technique to induce any kind of simulator sickness. So the measurement would be SSQ questionnaire, and we want locomotion to induce less cognitive load, because most of the times locomotion is kind of a primary task, something you don't want to think about, so it has to induce less cognitive load. So to measure that, we have NASA TLX, which is task load index, and so we came up with something called TriggerWalking, which uses spatial handheld controllers to navigate in environment, and we think that it is realistic and it kind of covers some of these factors. So I have a video which explains TriggerWalking. Yep.
In contrast to walking in place techniques or leaning gestures, trigger walking is a low-fatigue user interface. Trigger walking is a VR locomotion technique which substitutes controller trigger pulls for physical steps in actual walking. The user holds the controllers in a comfortable rest position and alternates left and right trigger pulls to take steps. Stride length is controlled by slightly tilting the controllers upwards. Movement direction is controlled with subtle yaw rotation of the controllers. The controllers are used in combination to execute gait cycles. The number and frequency of trigger pulls define the size and speed of the gait cycle. The technique can be used when the virtual environment is larger than a room-scale tracked space. Trigger walking can be used in both standing and seated positions. We performed kinematic analysis of head oscillations when users walk with an HMD. The task was to walk along the pavement at a normal walking speed, head position at each frame.
Sorry about that.
We performed oscillations to further analyze head oscillation. We included 4 different head oscillation conditions based on our initial analysis. The first was camera motion without any oscillations. The second one shows camera motion with only vertical camera oscillation. The third one uses vertical and lateral movement. The final camera motion includes vertical, lateral, and fore-aft oscillations. We performed an experiment to evaluate the effects of biomechanically-inspired LUIs on task performance, as well as spatial awareness and cognition. Participants had to perform a triangle completion task after they virtually walked along 2 edges of a triangle. A first target was displayed at a predefined distance with a random angle from the initial position. When the participant reached the first target, a second target was displayed 90 degrees either to the right or left. After reaching the second target, the participant had to point a ray coming out of the right controller to the estimated initial position and confirm it by pressing the touchpad on the left controller. In essence, while we could not find any significant influence of the different head oscillations on accuracy for spatial judgments, the results show that users can quickly learn the trigger walking technique and significantly improve over time. Furthermore, users feel slightly more presence, estimate the sensation of walking as more realistic, and perceive less cybersickness when biomechanically inspired head oscillations are used. Details can be found in the paper.
So that was the video on the 2 studies we conducted, and to improve the realism in walking, we kind of included camera motions. To do that, we first analyzed the HMD oscillations. So the task was there was an environment which is a plain grass field like the one in the picture, and there was a plank in front, and the users had to walk forward and backward 6 times so that we could calibrate the amount of head bobbing users had while they had HMD on the head. So we had 13 participants, and the vertical displacement was from 4.4 centimeters to 13.8 centimeters, and there was a lateral displacement of 3.91 to 7.68 centimeters, and 4F displacements of 1.56 to 3.83 centimeters. And we had the data of all the displacement for the frames, so we did a curve fitting for that, and these are the equations we tried to fit, and I promise these are the only equations that's there in the presentation, so no more equations. And so DV, DL, DF are the camera displacement in the vertical, lateral, and 4F directions, and AV, AL, AF are the amplitudes after fitting the curves. So we have used these numbers back in implementing trigger walking. And what is trigger walking? So it wasn't a technique which we implemented out of air. So we were trying out the teleportation because it's popular, it was already there everywhere. So to move a little, we had to teleport a little. So we were doing that and thought it looked more like walking. We thought we could kind of do the gesture, and it might kind of substitute the controllers for the legs, so that it can be described more like a micro teleportation, but it's not sudden. We used a love function so that there's an acceleration and deceleration, and so that it would be more realistic. And it uses the concept of natural walking, of taking steps, so we think it's after using it, it might feel more realistic. And it replaces the legs with the triggers of common spatial VR controllers. So we did an experiment to see the usability and if there is a difference between the head oscillations, or if the head oscillations improve presence or realism. And the task was a triangle completion task, as you saw in the video. So the user starts from a starting point, and a target would be displayed in a random angle, either with 5, 10, or 15 meters, and the user have to go there, and then and the next target would be displayed either to the right or the left of the first target, and the user have to go walk to by walk, I mean use the trigger walking to go to the second target and point towards the starting position. So it forms a triangle, so it's a triangle completion task, and we did a within subject design. So, and since we had 3 distances, and so we had 2 by 9 by 4 trials, 72 trials for each participant, and we had 24 participants. And the measures we had were, for presence, we used iGroup presence questionnaire, and for the workload, we used NASA TLX, and for simulator sickness, we used Kennedy Lane SSQ. So hypotheses, so we hypothesized, the first hypothesis was that participants will underestimate travel distances. In most of the previous work we see in locomotion, they found that users seriously underestimate the distance and size of things in virtual environments. So that was our first hypothesis. And the second hypothesis is that participants will significantly improve their performance with trigger walking across trials, which means that it is a technique which is easy to learn, and as the round progresses, they may improve their performance. And the third hypothesis is that when we have head oscillations in the walking, it will reduce the errors in spatial judgments compared to no head oscillation condition. And the fourth hypothesis was when we have simulated realistic head oscillations in walking, it will increase perceived realism of walking motions compared to no head oscillations. So the results showed that participants significantly underestimate the distance by an average of 3.88 meters across all the distances compared to the real distance. This was all across the 4 conditions, and so the H1 was confirmed. There was a significant effect for number of rounds. By this I mean that for compared to round 1, round 2 was better, round 3 was better for most of the participants. So H2 was confirmed, and there was no significant increase or decrease in the absolute error in angle estimation for different head oscillations. So H3 could not be confirmed, and there was no significant difference between oscillation types for the sense of being there or cybersickness or realism when compared to the condition where there is no head oscillation. So H4 couldn't be confirmed. So as I mentioned in the previous slide, the task completion time reduced as the number of rounds, like compared to the round 1, the time taken for round 2 was less and so on, but the absolute distance error was almost the same, so the users made the errors in spatial judgments almost the same in all the conditions. So the discussion from this study is that it seems that there is less physical demand and frustration while using trigger walking, and users could quickly learn the technique, and there was a significant distance underestimation, and condition 4R, which means the vertical, lateral, and fore-aft oscillation was induced more presence, and it was more realistic, but the significance or the difference was not statistically significant. And so since we had a study on the oscillations with no oscillations, then we tried to evaluate the usability of trigger walking compared to the other existing famous locomotion techniques. One is the joystick, so we used an Xbox controller, and the second one is teleportation, and the third one is walking in place, where you use walking gestures to move in virtual environment. So in the confirmatory study, we compared with the 4 conditions, trigger walking with 3 other locomotion techniques, and there was the task was there was an indoor scene, indoor house. If you have looked at the demo upstairs, you would have recognized this, and there were 12 Easter eggs placed inside the house, and 6 of them were easy to find, 4 a little difficult, and 2 were hard to find. So the task was to collect all the 12 Easter eggs in 3 minutes. So these are the results for the confirmatory study. So there were 16 participants, and the mean number of eggs found were 9.6, and we have SS scores for all the 4 locomotion interfaces, and you can see that trigger walking and teleportation have almost the same scores. And for the physical demand, there was statistically significant difference in physical demand between teleportation and walking in place, and trigger walking and walking in place. And based on pairwise comparisons, there was a statistically significant difference in cybersickness between trigger walking and joystick condition. And when we asked about which technique the participants preferred, 12 out of 16 participants preferred trigger walking to all the other 3 locomotion techniques. So in summary, we want a locomotion technique which doesn't make us tired or puke. So we came up with something called trigger walking, which is biomechanically inspired, and we think that it induces less fatigue and simulator sickness compared to artificial locomotion, and it induces less fatigue compared to real walking or natural locomotion interfaces. So, but trigger walking is something which is very maybe useful in a scenario like a medium distance travel, but if you want to travel longer, then we don't think it's a good idea to pull your triggers all the way. So maybe you could just use teleportation, but this is a technique which can be used in indoor scenes where you want realistic, where the task is to explore the environment. So a final solution could be to have set of locomotion techniques rather than just one, because we think there is no locomotion technique right now which solves all the issues. So having a set of locomotion techniques may be the solution for this issue, and that's my PhD thesis gonna be. So yep, so any questions? Thank you.
So, do we have any questions?
I'm really surprised by your results. How much of this is, and at least the second set, do you think was dependent on the task, like the indoor environment where you couldn't travel long distances, that wasn't even really an option?
Because the scenario is that we thought this one would suit somewhere where you have to observe everything. So trigger walking was much preferred because of that, because if people were using teleportation, they were kind of disoriented and they couldn't find the eggs properly because they couldn't observe the environment well, so they were disoriented. So I think the results are because of how we designed the experiment, to like the scenario we created. Yeah.
Thank you so much. So I have a question about environmental setup. So while you are sitting and you want to use this technique, do you think that you need some kind of a special chair for that, some stool chair, so you cannot, I don't know, sitting on this kind of chair and using this technique? Yeah. So what do you believe that? So this idea needs its own setup. I don't know. Maybe I'm just thinking about that. So it needs its own setup. So it's not really comprehensive that you can use everywhere or in every scenario.
No, it is not a comprehensive technique. That's what I was mentioning in my last slide, that it is not useful in all the scenarios, and while sitting you can still use the technique, and as you said, it is good to have a swivel chair where if you want to turn around much better, but in this technique the direction of travel depends on the direction of your controller. So if you want to go back, you can just point your controller back. So swivel chair is not a necessity. You can still do that. You can still navigate in all directions without having additional hardware. Yep.
Thank you.
Okay. Normally, if I want to walk fast, I'm both increasing my gait frequency, so I'm stepping faster, and I'm increasing my step size. And you've decoupled it in your interface, so you're using the orientation of the controller for the step size and the trigger frequency for the gait cycle. Why did you do that? Why are you decoupling them and not just using one gesture for both of them?
Because it gives kind of a control of motion, because some people say, as I said, this technique was developed by doing micro teleportation. So if I want to go only a little far, then I just use a trigger pulse, it's more like to be precise. So if I want to go somewhere and I want to be very precise, then I would just have more trigger pulls rather than having large straight length and go collide with the walls or something. So it's the same kind of control we have in our own walking. So that's the reason. So you can have a small step or you can just have larger steps. So that's the reason we have, yeah.
So with
And moreover, if you pull the triggers too much, or if you use this thing a lot, you may get finger fatigue. So we think it's a good idea to have like a control of speed by increasing the straight length.
okay, just a quick follow-up. Did you observe that the user actually coupled the orientation and the trigger frequency? So it was on your video that the user who was wanted to go faster and pull the controller down and start triggering faster
Yep.
at the same time. So did you observe any consistency in this regard? between
It sometimes people just hold the triggers in the maximum straight length because for some reason there's a natural way of holding the trigger. So I have to mention that this is the rest position. So you have to keep there. But I have observed that if people want to go faster, they would just like have the maximum angle orientation and trigger faster. So, yep.
Okay, thank you.
Thank you.
So Rob asked me why I was surprised earlier. And I think my big surprise, yeah, so what was surprising was that people didn't get horribly sick. That was my big surprise is why people didn't get horribly sick. So like number one on the Oculus developers guide back in 2013 was, don't use head bob, right? Like that was a bad thing and you guys used head bob.
Yeah.
And I don't understand.
The head bobbing, there's a trade-off, so we kind of calibrated and it's very subtle. So when it's subtle, then it doesn't induce a lot of motion sickness, but if it's a lot, like if you can feel yourself moving up and down, then yes, it induces motion sickness. And also if the user is using artificial locomotion, for example, joystick, and if there's head bobbing, it increases cyber sickness. So, but this is more like a controlled movement. So we can compare it to the driver in the driving seat and the passenger in a car. So if you are driving, you have the control of motion, so you don't feel motion sickness. But if you are a passenger, you don't know if there's a rotation, or so people get disoriented. So since you have that motion, then head oscillations, they don't induce any kind of sickness, at least in this technique. So yeah, maybe that's the reason.
So with the joystick condition, were you using the head tracking for direction, or was it how was that set up? Was it rotation with the joystick? Or?
It's rotation with the joystick.
Okay, so.
But yeah, the gauge and the direction of the gauge, so you can just, head directed, like wherever you look at, you move in that direction using the joystick. The thumbstick.
Okay, so there's no rotation with the joystick?
No.
Okay.
No. It's notorious for, the rotation is notorious in inducing, most of my participants already felt sick just with that joystick movement, and I thought it isn't a good idea to give an additional rotation where it makes people sick, so.
So you were just pressing forward, basically?
Yeah.
Why do you think that there was such a higher amount of sickness, cyber sickness, than versus?
Even the basic motion using joystick makes people sick, because even I'm sensitive for this joystick. So while coding, I had to code, have a speed, then move forward. Sometimes I had to lay back because I was feeling sick while testing it. So it was that bad. And because the body says, or the visual says we are moving, and the body says we are not moving, so that's the main reason for the simulator sickness, because of the joystick. So even without the rotation, if there is a linear acceleration, then it makes people sick.
Okay.
Yeah, so the rotation is like an added bad thing.
Yeah, okay.
Yeah.
Thanks.
Okay, One last question.
I don't have a question. I just have a comment on moving the camera. So the first-person camera. So for the locomotion technique, I guess it's inevitable. We should use this technique, but how we design our environment, or so the techniques. There are several techniques that we can reduce the cyber sickness, just like the changing the field of view, or having some kind of the realistic walking and the animation, the speed of the camera, what kind of speed that we have. So I guess part of this problem is because of the design of the environment. So I guess maybe in the future they can add more techniques that control the cyber sickness and the speed. But I guess it's inevitable for first-person character. We should move the camera, and most of the head-mounted displays, so they're just coming with some kind of the joystick controller that you should sit on the chair and move the camera. So yeah, this is a problem. That's some kind of